Hello, everyone. Hope all of you are doing well. Thanks for joining this webinar. As you all know, this webinar is a part of our weekly webinar series on geoenvironmental engineering. So I want to introduce our presenter today. Our presenter today is Dr. Phil Carpenter. So currently, he is a professor of environmental geophysics, engineering geology, and seismology in the Department of Geology and Environmental Geosciences at the Northern Illinois University in DeKalb, Illinois. It's not too far from Chicago. Actually, it takes less time for me to go to DeKalb than going to my office in Chicago. So he's very close to me. He teaches undergraduate and graduate courses such as geophysical well logging, groundwater geophysics, applied geophysics, geophysical field methods, reflection seismology. So all interesting topics for us. His research includes hydrogeophysics, geophysical assessment of karst features, landfills, mineways, and detection of pollution, and also earthquake history and occurrence. So he has conducted many projects in the US, Mexico, and China. Some of these projects include geophysical imaging of karst features, geophysical assessment of landfills, and detection of pollution, earthquake history of Northern Illinois and Southern Wisconsin. So his research has been funded by many agencies, such as Fermi National Accelerator Laboratory, US Department of Energy, US Geological Survey, US Department of Interior, Society of Exploration Geophysics Foundation, National Science Foundation, and industry. So he has published many papers in reputed journals and conference proceedings. He is active in professional societies such as Environmental and Engineering Geophysical Society, Geological Society of America, American Association of Petroleum Geologists. On a personal note, I have known Professor Carpenter for more than 15 years now. I can say that he's an amazing person, very kind, very humble, very modest person, but he is very smart and dedicated geophysicist. I worked with him on a project, a bioreactor landfill project a few years ago. I learned a lot from him. One thing he taught me is that in geophysics, I always remember this, the easier the geophysical testing is in the field, the harder it will be the interpretation of the results. That is the lesson I learned, because in the field, he would show me on the screen that, see here, there is a liter recirculation pipes underneath, 15 feet deep, 30, 20 feet deep. But he could only find that one. I was not able to figure it out on the screen. So that shows that, geophysics expertise is needed to interpret the results. So it's always pleasure. It's always pleasure to spend time with Professor Carpenter. We had attended some conferences together. So it's always pleasure working with him and meeting with him, spending time with him. So Phil, with that introduction, take it up.
Okay. Everybody can see the screen okay, right?
Yeah.
Let's go ahead and move on. I do want to apologize. This is not organized perfectly. I'm going to probably update this presentation. My email is on there. So if anybody wants to contact me, for more information, it's there. pjcarpenter@niu.edu. Okay. So we're going to be looking at 3 sites here. My very first project in Illinois was looking at the Mallard North landfill, Hanover Park, Illinois, and then Argon 800 area landfill, and then the Orchard Hills landfill, which I worked on with Krishna a lot. That was actually his project. So we'll be looking at those 3 sites. Just a few things about the geophysics. When you're doing geophysical work, everybody can hear me okay? Right.
Yeah, it's good, Phil. Yeah, we can hear you.
Some of the things you want to do is define the target, with the appropriate method. I wonder if I can get this thing working. I don't know if my pointer's working.
Yeah, it's working. We can see the cursor. Yeah.
Okay, good, excellent. Define the target, select the appropriate method. That's really important. Review any kind of previous work from your site. This is really important to model the expected response of your target, okay, before going into the field. Because if your response is too small, you're not going to see anything. So that's really important to do that. So the first three steps are before you actually go into the field. Then you finally get into the field. You need to interpret your data as you're collecting. So, you know, you can collect your data in the morning and look at it over lunch just to make sure it looks okay. So you don't have a problem with your instrumentation, or you might encounter something you don't expect. And you have to change your field orientation to deal with that, like your station spacing. Finally, the fifth stage is formulate physical models, identify and quantify uncertainties. And then finally, review the model accuracy based on other information at the site. So this could be borings, test pits, outcrops, stuff like that. Okay. There are, limitations with geophysical methods. You generally can't use one method to do everything. So you need multiple methods. Sometimes the theory is really complex, especially with electromagnetics, where you got Maxwell's equations. So interpretation can be difficult. A basic rule is resolution decreases with depth. So the deeper you go, the less detail you can see. Models are often non-unique. We'll see some examples of that in these cases I'm going to show you. Sensitivity to noise is a biggie. And that, especially in landfill situations, you got trucks moving around and sometimes electrical noise. And then boreholes are usually required, both calibration and validation. Actually, I don't have any information, any borehole data for you on this presentation. I was going to add that. I never had time to add that in. But subsurface information is very, very important to validate your geophysical interpretations. So final geophysical report would include these kinds of things. And a lot of you will be hiring contractors to do this work. Make sure you get the data. That's the main thing. And make sure the report has these kind of elements in it. So we're going to be looking at different levels of sophistication, basic resistivity soundings, and profiles. That'll be the first example from Mallard North Landfill. 2D resistivity, electromagnetics, we'll be looking at that at Orchard Hills, and EM at Argon National Lab. 1D refraction, we'll look at a little bit of that at Mallard North. So these are the three case histories I'd like to include. So we'll start with the Mallard North landfill. And that is located in Hanover Park, Illinois, just outside of Chicago. It's not a really great picture of it, but that's where it is. And a big problem with this landfill was fractures. So it was built like in 1974 or something like that. Not properly lined. I don't know if there was any liner underneath it. And the surface was fractured heavily. So these are the fractures here. You can see in the top diagram. These are monitoring wells and gas vent wells. And actually, this was quite interesting because I actually went there they had these gas vents that were flaring the gas out. I took one, there was one that was capped, and I actually took the cap off and it blew off the top. And then I listened, and there was like this boiling water inside of it. So the interior of the landfill was something like 98 degrees or something like that. It was very hot. So here's some of the lines we did. Seismic lines and resistivity lines are shown in the bottom diagram. So the shorter lines are the seismic lines, the longer lines are resistivity lines. So these are resistivity soundings that we did to try to interpret the interior of the landfill using resistivity methods. Let's move on here. Okay, so this is out of order. Way out of order. Let's see. Okay, they're getting back to resistivity. So soundings expand electrodes around the center point, and they map vertical changes. Profiling moves electrodes along a line. Azimuthal surveys rotate the resistivity array around a circle-like type pattern. 2D surveys combine sounding and profiling. We'll see that for Orchard Hills. 3D surveys are very seldom used. My experience, working in China and in Mexico, where there's very limited equipment, is sounding is the main method used. So that's, again, expanding electrodes around a center point or moving them along a profile. So the 2D surveys require specialized equipment. And I think we'll get some pictures of that later here. So we'll see. So this is, these are some of the results from our soundings done at Mallard North. And you can see you've got refuse and fill over gray silty clay. This is basically Wadsworth Formation. These are the resistivities. So this is in ohm meters, 61 ohm meters, 12 ohm meters, and 30 ohm meters. When you get to the leachate saturated materials, you get really, really low resistivities. So like 3 and 4 ohm meters, that's definitely telling you you've got leachate. Leachate is very heavily, it's salty, basically briny water, a lot of dissolved solids. And here's just a picture of it. Let's see. This is showing the water levels and the topographic information. And again, this is typical electrode geometry. So A and B are the positive and negative electrodes. M and N are the potential electrodes. So the current goes from A to B. A is the positive, B is the negative electrode. There are 3 basic types of arrays that we use. The Wenner, sometimes called the Venner array, where everything is equally spaced. The Schlumberger, it's not Schlumberger, it's actually Schlumberger, where the MN is really close together, the AB is separated. And then finally, the dipole-dipole. So the dipole-dipole is used mostly for 2D work. The Wenner and the Schlumberger are used for 1D work. Again, I apologize for this lack of organization on this. I'm actually going to restructure this a little bit. But here's an example of the sounding that we got at one of the locations, Mallard North. So we have this kind of a sounding curve. So this, you've got spacing. So this is the spacing of the electrodes. And this is the apparent resistivity. So here's, this actually is from another site, but it kind of illustrates what we saw at Mallard North. So what you do is you have the sounding curve over here, and then you invert that using a computer program for layered models. So this gives you, this is like a 1D, one-dimensional type of thing. The next one, let's see, there's one of my students actually collecting data. So you can actually see the electrodes here. These are these steel stakes. And then here's the wires, and then here's the unit, actually. That little orange device has a battery in it, transmitter and receiver, so it collects the data. Let's see. Ah, here we go. Okay, so this is the sounding over Mallard North. So what we got again is spacing, and then apparent resistivity, the model, and the interpretation of the model. So we have cover, refuse with leachate, and then Wadsworth till underneath it. And those represent 4 layers here, with depths going down to about 30 meters, more or less. So this is the actual curve we collected. This is the model from the computer inversion. And this is the actual interpretation. In the old days, we actually did the model using curve matching. And when I first came to Northern, that's what we did. We actually had this big pieces of paper, and we'd plot the curve out, and we'd match it. You'd actually go to a light table, and you'd lay it on top of a type curve, try to match it. Nowadays, of course, we do it all on the computer. So, let's see. Okay, so I'm just going back here one step. I've done a lot of work in South China, and we've seen things like this. This is adjacent to the Maoming landfill, Maoming, China. It's in Guangdong province. And you can see a really big dip in the resistivity here. And when you interpret that, you have, okay, the water table's right up here, right? So that's what at 1 meter, it's very shallow. And then you've got this incredible drop in resistivity between about 4 and 8 meters. And that's the only way I can explain that. When you look at, let's see, it disappeared. Let's go back. Okay. The only way you can really explain that lower resistivity, that's 10 ohm meters, is something's polluted. Normal water is not going to be that low. So what this was a village that had polluted groundwater. We found it by doing resistivity soundings, but they knew it was polluted before that. We just wanted to identify the depths where the pollution was coming in. And again, it was a landfill, and the leachate was moving down into the aquifers. And then these were actually artesian aquifers, so it was actually coming back up into the wells in the area. So there's a lot of good stuff you can do with geophysics, around landfills, not only on landfills, but around landfills. Okay, Argon 800 area landfill. I'm not going to spend a lot of time on this, but this is Argonne National Labs down by Bolingbrook. So on the landfill itself, we did several resistivity soundings, and we did some electromagnetics. So to show you some of the sounding lines we did. One of the things about this landfill was they had a French well, they call it a French well, where they poured about 35,000 gallons of liquid waste, trichloroethylene, and other kind of organic waste into the ground. And where it went, nobody knows. So as part of our objective was to find the French well, which is like a corrugated aluminum housing, and then they had a bunch of gravel inside of it. And they did this in the 70s a lot. There's also a bunch of wells around this perimeter here that we looked at to try to compare our results. So let's see. So we did electromagnetics at this site. So EM involves a transmitter and a receiver. So you've got two loops, two coils, literally. And what happens with the transmitter is it generates a magnetic field, which induces a current into a conductor, which produces its own magnetic field, which gets picked up by the receiver. So you've got what's called the primary field here, and then you have what's called eddy currents, and this is the secondary field. So you can tell what the conductivity of the earth is. And the nice thing about the EM is you don't need ground contact. You can actually do this above the ground from the air. You don't have to plant electrodes in the ground. So that's kind of nice. And this kind of goes through it. Simple field procedures. Unfortunately, the equipment's very, very expensive. So the basic unit that we used cost about $30,000 versus the resistivity, which you can actually build a resistivity instrument for a few $100s. So it's kind of a big difference in price. And you get interference from pipes, power lines, fences, etc. So there's two basic methods for EM. One is called time domain. The other one is just basic profiling. So you can use EM methods to do the same thing you do with normal resistivity. It's just more expensive equipment. Personally, I like the time domain systems. We've used those in Mexico to look for the saltwater freshwater interface. It's really worked well, but it is expensive and it requires, expensive software to analyze. Again, the direct current stuff there's actually lots of free software for that. You can contact me if you want some information on that. There's actually somebody at Wheaton College that designed a system you can build for like $500. He's also got free software. So EM is a little different. You have to actually buy proprietary software to interpret the data, unfortunately. So it uses induced currents in the shallow subsurface. There's your picture again. There's a bunch of other stuff too here. Typical EM methods. Okay, so the frequency domain is the one that we used. Let's see. This is what we used at Argon, and we've used this at Orchard Hills too, which I'll be talking about. Time domain. I've not used this in Illinois. I've used this in Mexico. Magnetic tellurics. I don't think I've ever. Yeah, we've used this a little bit. When I was working in industry, we used AFMAG in Texas to find uranium deposits. And then very low frequency, VLF, we have an instrument to do that here in DeKalb. That is interesting. It works sometimes, and sometimes it doesn't. We've actually found archaeological artifacts using VLF. So it's kind of interesting information, method. So here's the Argon landfill, the Area 800 landfill. And I was going to add another picture to this, and I couldn't find it. But the French terrain is right here. So these are terrain conductivity, called terrain conductivity. This is in millisiemens per meter. And it's pretty obvious where the drain is. So the rest of this stuff, there's something else going on over here as well. I think these are buried pipes here, but this is where the French drain was. So this does work. And these little dots are where we collected data. So this again is, it's adjacent to Waterfall Glen. Some of you probably know where that is, Park District and Argon National Lab. So this is like on the edge, Westgate Road of Argon. Okay, moving on to Orchard Hills. So this is where we did a lot of work. This is located in Davis Junction, Illinois. About, let's say, 100 kilometers. Yeah, about 100 kilometers west of Chicago. Approximately 67 miles. So there were numerous parts of the landfill here that we looked at. This part of the landfill was a leachate recirculation area in the northern portion here. And we did some profiles on the older part of the landfill as well. So here's a nice picture of it, contour map, lots of details here. So LRL are the leachate recirculation lines. Let's see, there's gas extraction wells here, here, and here. And then these are the resistivity lines that we did. Actually, I didn't do them. They were done by another researcher. And then these are the gas extraction lines here. So a lot of detail on this map. So this is kind of the north. I'm going to put back here. So that map is this area right here. And a couple of cross sections here. Solène Grelier did she did most of the work on the resistivity. Here's LRL 28. This is a leachate recirculation line right through here. This shows you kind of the profile of the landfill as well. So we're talking about LRL 28 being 12 to 15 meters below the surface. LRL 29 shallower. Again, flip back here, you can see where these are. There's LRL 29, LRL 28 right here. So one of the things we did, and Solène did this, she buried electrodes below the cover of the landfill and over time recorded the resistivity changes with a system kind of like shown here, where you have multiple electrodes. You can maybe see them here. They're programmable and they all attach to a computer here, right? Let's see, there's one of my students doing the same kind of work in another site. But that was buried in the landfill. So all the data comes to a system like this. This is called the Sting R1 system. She used a slightly different system, but it's powered by a battery and the data is downloaded to a computer. So this is what she saw over time. So as the leachate was being recirculated, she actually saw changes occurring in the landfill itself. So you can see here, this is the original data. So 1 hour, 7 seconds, 7 minutes after recirculation, you start to see some changes. What you're really looking for here are changes in resistivity. So this is all in relative values, but she saw this area here develop. You can start seeing it here. This is a gas development area. So gas is actually being generated by the leachate recirculation. So that's pretty interesting. Seismic tomography. So this is something else we did at Orchard Hills. And this was done with basically by Mike Thompson, who has a consulting firm in the Bolingbrook area. So seismic refraction tomography involves a number of steps. Refraction, I've got some pictures which I think were earlier, which we'll flip back to. You basically pick first arrivals, enter them into a data file, plot the data on a time distance graph, examine for errors, choose an initial model, usually based on some kind of layered model to start with, and then discretize the model. So it basically breaks the subsurface up into little blocks and tries to figure out the velocity of each of those blocks are. I'm going to see, let's see. So here's some more information on that. So basically you're looking at the Earth like this. So you're firing these seismic waves through the ground. You're turning the Earth into little blocks like this. And then you're figuring out the velocity of each block. They call them velocity cells. And I'm going to flip back a long way back here. This got out of order. Got some seismic stuff. There we go. All right. Yeah, so, okay. And I will fix this later in the revised version. But seismic refraction involves a shot point here, and then you have waves that refract upwards. Seismic reflection involves just reflection of waves. Typically, okay, so this is a good example of that. Seismic reflection, the waves go straight down and bounce back up. Refraction, they actually refract along this boundary down here. Let's see. And they generate other waves that come back up the surface. So this is the refraction is the method that we're using. So the field layout is you hit basically a plate with a hammer. The waves go down and then they come back up at some point. And this is actually what the data looks like. So the field, and what you're basically interested in with the refraction are the first arrivals. So the very first arrival of the waves, that little tiny little blip there, that's what you want. The rest of the stuff is stuff like surface waves or reflected arrivals. And there we go. There's a student doing a refraction survey. So you can see he's hitting a plate here with a hammer. This is a little more sophisticated. We're actually not allowed to do this anymore. This is a downhole shotgun, which produces more energy into the ground. But they don't really care for that right now. So we took that apart. And here's another method hitting a plate on the side generates what's called an SH wave or an S wave. And we use that over Orchard Hills. And then this is a geophone where you can see, so this is the sensor. So this records the vibrations and it goes to a cable like this, which is these are called takeouts. And then this goes back to the recorder. And so you'll have a line of geophones like this, usually. Now in the Orchard Hills landfill, we had a set of geophones on one side, and then we had plates on. We actually hit the plates on the other side. So you end up with a graph. So this is the kind of the geometry of what's happening, and then this is the graph of time distance. So again, those first arrivals we talked about, if you plot those up, you'll get a graph like this. So this is the direct wave, this blue thing here. And this is the head wave or the refracted wave. This is for a 2-layer model. Obviously, we have a little more complexity at Orchard Hills than 2 layers, but this is what you normally would see in a typical situation. And if you have more than 2 layers, you'll see something like this. Okay. And again, I'll try to fix this PowerPoint so that this stuff is in the proper place. So there's a number of methods you can use. Delay time method, GRM, seismic refraction tomography, which is what we're using at Orchard Hills. Look at the interior of the landfill. Okay, so I'm going to jump ahead here. Okay. So we're back to the tomography at Orchard Hills. Yeah, so we inverted the data like, there it is, okay. Basically breaking up the interior into these little cells. And we determined the velocity of those cells, which can tell us what kind of materials we have. The velocity depends on the shear modulus, the bulk modulus, which is really important in landfills. Especially these kind of leachate recirculation landfills, because you're getting deterioration of the waste over time. And that changes the shear modulus, the bulk modulus, which can affect the dynamic properties of the landfill. And there have been cases, where there's been collapses, slope failure, and things like that in landfills because of that. Skip over that. Some more background. Again, the order on this thing needs to be fixed. Okay, so here's our shot points. So this was on the west side. Our geophone array was on the east side. So here's your cap material, your cover material, and your waste is inside here. So your shot points would fan out like this. These are kind of idealized wave patterns. But this is pretty accurate, actually. Pretty accurate measure of what it would look like. So we did, they call this a fan shooting. So you're actually doing, these kind of look like fans here. So it's not classical refraction. It's just, you're just basically shooting through the waste. Which is interesting, you can do this, and landfills offer you this opportunity. So here's the S wave velocity map. So this is the shear wave velocity. And you can see some changes here. So you've got this material down at the bottom has a little bit higher velocity. The material up here, less velocity. Again, here's your geophones, and then here's your shot points. And the vertical exaggeration is 4 here. Let me go back here. P-wave velocity is more interesting, in my opinion, because this involves the bulk modulus and the shear modulus. And it's more representative of the mechanical properties of the waste. And you can see a definite change here. So you've got this higher velocity material down here, and the velocities are over on the far right. And then this material up here is lower. So there's a big boundary right here at about, I don't know, 246 meters, something like that. This is again a leachate recirculation landfill. So you've got degradation occurring here in the waste material, and mechanical properties are changing. Let's see. And then you could take the P wave and the S wave velocities and compute Poisson's ratio, which is kind of interesting. For normal rocks, Poisson's ratio is about 0.25, but here it's much higher than. You can look at these numbers, like this blue-green stuff is about 0.4, 0.42. So Poisson's ratio ranges from 0 to 0.5. And the higher the Poisson's ratio, the less rigid the material is. And again, you can see this big boundary right through the middle of the landfill right here. Which is kind of interesting. Okay, let's see. Let's get on the radar. Okay. So GPR is one of my favorite methods, ground penetrating radar. So just kind of some background information on GPR. It's very, very important to have the correct frequency for your system. You do not want, for geology stuff, you don't want anything higher than 200 megahertz. And the lower frequency, the better. So lower frequencies give you low geological targets, deep penetration. Unfortunately, you have unshielded antennas, which means there's a lot of noise that can come in. High frequency systems are designed for rebar concrete pipes. You probably have seen these on the highway or on the tollway, where they're dragging an antenna behind a vehicle to look at concrete. You don't want that system. If you get into GPR, you're going to want something below 200 megahertz. And we like to use 50 or 100 megahertz antennas. And here's some examples of GPR. If you have a flat area, you could have a cart like this. These are two look like 100 megahertz antennas. Our system is more like this, where we have two that you manually move, simply because we work in a lot of areas that are not flat, and a landfill would be an example of that. So you actually will need the separate antennas like this. These are 100 megahertz antennas. So if your antenna is really small, it means that you're probably above 200 megahertz, and you don't want that if you're going to do landfill work. It's very important, actually. If a lot of times you rent this stuff, it's very, very important to tell the vendor what you want, because I've had students that have called me in a panic. They got like a gigahertz antenna because they didn't specify the frequency. And you can see about this deep with a gigahertz antenna. So it's really important to specify the frequency. So if you have a situation, you know, let me, if you're in a landfill situation, let me know. I can probably give you some advice as to what frequency to use. So this is ours. These are the 100 megahertz. Actually, these are the 50 megahertz. So there's one unit here with a transmitter, one with a receiver, and then you can maybe make out the antenna right here in the grass. And you got these fiber optic cables. And the reason they're fiber optic is to keep metal away from the whole system. So you don't want metal anywhere near this if possible. And then way back here is the console box. There's a battery in here, and then a computer record everything. So these fiber optic cables go all the way back down to here. And then these are fiberglass PVC pipes here. There is some metal inside these two transmitter receivers. These are actually lined with foil, so they're like a Faraday cage, so you don't get interaction, and they do have batteries. Unfortunately, the batteries are the big problem with the system, as well as the fiber optic cables, which you can step on and get broken very easily. Okay, so this is a typical GPR signal. And let's see, this is from Orchard Hills. So the first two signals you'll see are the ground wave and the air wave. So those are generated by, the air waves generated by the signal going through the air, ground wave through the upper few centimeters of the soil. And then you start to see the top of, you actually start to see some real stuff below that. So this was an example that we did over part of Orchard Hills. We saw the refuse just below the clay cover. You can see the air wave and the ground wave are very uniform. They're like perfectly horizontal. Below that, you see some choppiness and irregularities. That means you're really seeing some real data. You're seeing some real stuff below the surface. We went over most of this already. Okay, we're not doing well logged. It's out of order again. Again, I'll put this back where it belongs. This is supposed to be in the Argon section for some reason. We use this instrument. This is an electromagnetic device. So you got a transmitter and a receiver. And there's a picture of these coils. That's the transmitter and receiver. You can put them in different orientations to get different depths. This is called the vertical dipole because the magnetic dipole is going straight up and down. This is the horizontal dipole. The dipole is going sideways here. Again, the magnetic dipole is perpendicular to the loops. And there I am at Argon with EM31. So the transmitter on this side and the receiver on that side. So there's different devices for EM. We'll skip over that. Okay, so yeah, we did this. should jump down to the GPR section. Yeah. So the GPR involves frequencies in the kind of the FM band, 100 megahertz. This is the GPR range here. So just to kind of give you an idea where we are in the electromagnetic spectrum, visible light is here. So that's about 10 to the 15th hertz. So GPR we're between 50 and 1,000 megahertz. So we're basically in the, we're in the range of, FM stations. In fact, you can't do GPR if you're a radio transmitter. So again, this is kind of an idea of what it's doing. You've got a transmitter, receiver. You basically drag it across the ground, or you move it manually. Sends a signal down into the ground, bounces off layers. So these are radio waves, essentially going down into the ground, bouncing off different layers. And you'll typically see something like this on the bottom. This is actually a very old radargram. Nowadays, things are much cleaner than this, but you'll see layers. And again, at the top, you see the air wave and the ground wave, although it's not very clear in this example. This is a nice diagram, actually, I use in class. Direct air wave goes from transmitter to receiver. Direct ground wave does the same thing, but it passes through the upper part of the ground, generally within 10 centimeters of the surface. And then the direct reflected wave goes down, hits some kind of boundary, and then comes back up. So actually what you're interested in is the reflected. That's what you're after. Now these ER1 and 2, this is the relative dielectric permittivity of these different layers. That's kind of a fancy way of saying these are different materials. So it's kind of like refraction and reflection. Like you could, at the water table, you have a huge change in ER1 and ER2. So radar is a really good method of finding the water table or the bedrock surface, ER1 and ER2. So ER1, let's try to think, like in unsaturated materials, it's probably going to be about 10-ish. ER2, it's going to be about 30 saturated. So there's an increase of like a factor of 3. And the same thing in landfills. So radar actually works pretty well in landfill situations. So what you do is you move your units along a profile line. It's very simple, actually. You just move these. You have to keep the distance between the transmitter and receiver at exactly the same distance, but you just move them along a profile line. And you can convert to depth using this equation, z equals TV over 2, unless you're very close to the surface, in which case you have to take into account the separation between the receiver and transmitter. So it's a very simple method to use. And again, most of the GPR is done on carts nowadays, although on a landfill, I'm not sure that would work so well. So we've actually used Orchard Hills, I think we use 100 megahertz, 50 megahertz, and we even use the 25 megahertz antennas. 25 megahertz antennas are really large. So the 100 megahertz are 1 meter, the 50 megahertz, 2 meters, 25 megahertz are 4 meters long. So they're difficult to manage in the field. We covered all this stuff already. So here's some relative dielectric permittivities. We just kind of explained, water's got a very high dielectric permittivity. Ice does not. Actually, the radar works beautifully over glaciers. Air, of course, is one. Clays tend to absorb signals and have lower dielectric permittivity. And then the absorption levels for common materials are shown down here. So you're better off in mafic, felsic rocks, felsic granitic rocks. You're not going to use this successfully in a saltwater environment. And then glacial till, because there's a lot of clay in tills, diamictons. You're talking about 1 to 5 decibels per meter absorption. So you can do some calculations using these numbers to figure out how deep you're actually going to really see. And of course, in landfills, you've got a lot of clay, you've got clay cover and clay intermediate cover between the different lifts in the landfill. So actually, it's amazing this thing actually worked. We covered that already. So this is one of my favorite pictures. We actually saw a leachate recirculation line 28 at a depth of about 5 meters, 4 to 5 meters. And it showed up like at a fraction here. And it's hard to see in this picture. Actually, the colored version of this is much better. So again, the way you want to interpret this, the top thing is the airway, right? The second thing is the ground wave. And then the third thing is probably the top of the refuse below the cover. And then there's a few reflectors down here. And there's actually a diffraction here from leachate circulation line 28. So I think that's about it. Let's see. Again, I apologize for the lack of organization on this. There were a couple other, backing up here, a couple other things. This is some of the EM stuff we got at Orchard Hills 2. Yeah, so some of the EM stuff is back here, but I think that's pretty much it.
All right, Phil. You want to stop sharing?
Yeah, I can. Let's see.
Press the stop sharing.
Turn that off. I guess see some things in the chat.
Yeah. Can you stop sharing it so that way we can?
Yeah. Let's see.
You should be able to
Pause share. Okay.
Yeah. Stop sharing.
Stop it. Okay.
Yeah. So just I want all the attendees to type their questions in the chat box. So before Phil answers your questions, I just want to mention that I know Phil has been really busy these days, but I requested him to give the presentation so that the main purpose of is to introduce Phil Carpenter, Dr. Phil Carpenter, to you guys, because a lot of you work in geophysics, and I don't know anybody other than Phil Carpenter that knows geophysics, more in detail. And as I mentioned in my messages too, that he will be very happy to collaborate with you. And if you have any project, not necessarily in the US, but in other countries, if you have any project, please get in touch with him, seek his opinion, or have him come to the site and watch it, or have him do it, whatever. But get his help, because he has tremendous amount of experience. I just want to show you one. I want to share you this one picture. I wanted to show you before, but didn't get a chance. So I had a pleasure of working with Dr. Phil Carpenter on this project, as he was mentioning. Sorry about this. Just show this slide, just to make one point. Okay, here is the pictures. You could have put a lot of pictures, but so here's the picture of some photos of, not all, everything, of the work we could do together at a bioreactor landfill at at Orchard Hill landfill. For me, I mean, I didn't know anything about. I mean, I studied geophysics, but as I mentioned, it's one thing to study on paper, but actually doing it in the field is different. And also, as Dr. Phil Carpenter mentioned, it's easy to do it, but knowing all the details and interpretation of those is very, very important. So Phil Carpenter has the knowledge of these different technologies, and he actually does the work. So I just wanted to show these pictures to show that he does not teach; he actually does things. Here he's the one. Here, he's the one here. He's the one here. So this, as he was showing, GPR and EM and seismic and another EM method. So on this project, it was interesting for me to work with him, because the goal of this project was to determine which geophysical methods we could use to monitor these spatial and temporal variations that are happening in the waste. Because you don't want to go and drill it and collect the sample all the time and get that information. So we were thinking, if we can do this non-invasive manner and go and do it at different time periods and get idea of what's going on in the waste. So we learned a lot. And some of the other things that we did, Dr. Phil Carpenter didn't present, but we also did well logging using different techniques.
Right.
So I wanted to mention to all the attendees that keep his contact information handy. As he said, his email address is there, and this webinar is going to be recorded. But keep in touch with him on anything that you're working on geophysics.
Certainly.
Anybody who has questions, please. Do you want to see any questions in the chat box, Phil?
Yeah, I'm going to go through those. Let's see, I'm going through the chat box right